And our next keynote speaker, Benedikt Bunz, is going to introduce more about cryptography to us. While we are having a little bit technical problem, I would like to tell you a little story about our problem, our journey to compliance. So our team has been engaged in this blockchain community for more than 2 years now. And in early 2017, we were doing a project in Texas, and we got a call from SEC. And that was like a wake-up call to us, like, okay, regulation is coming. So, okay, let me tell you more about this story later, and let me hand this mic to Benedikt.
Okay, should I use this or?
Oh, sorry.
Oh, okay. Well, yeah, thank you very much. So I will attempt to, I feel like for some sort of cryptocurrency conference or workshop, there should be some sort of introduction, or I want to give a very brief introduction of how these things actually work. What does it mean? What are like some of them are? Let's look under the hood and try to maybe get some sort of understanding of how cryptocurrencies and blockchains and technology that powers them works. And I'll be focusing in general on Bitcoin because it's the first cryptocurrency, and in some ways it's a simpler one. And there maybe in the questions you can ask about the differences to other cryptocurrencies. But in general, the aspects that I'll explain will apply to all cryptocurrencies. And just about me, I'm a PhD student here at Stanford in the computer science department in the applied cryptography group. So why do we have cryptocurrencies, and what is kind of the thing is that even before cryptocurrencies exist, there was this allure of digital money and kind of this idea that what if you could send money just like you can send an email around the world without a lot of fees, just could we do the thing that email did for mail? Could we do that for money? Can we have e-money? And I will go into a little bit details why we have moved to more digital money, right? There's kind of Venmo and all these things, but if you ever try to do an international transaction with traditional money, you will know that these things are very difficult, and things like checks and are still very much around. Money is not digital yet in all of its aspects. And so why is digital money difficult? Well, one of the first things that jumps to mind is counterfeiting, right? What if you have someone can copy-paste money? And the problem is that with digital things, there's digital files are very easy to copy, right? It's very easy to take a file and make a copy of it, and then there's no way of telling which file was the original one and which one is the new one. So this is the problem that many people think of when they think of digital money and what makes it difficult. It turns out this is actually the easier problem to solve, and the way that we solve it is just kind of like we solve it in the traditional work with the signatures. So what do I mean? Well, so there's this thing that has been around since the late 70s, which is called a digital signature. And when Bob says, he sends 1 Bitcoin from Bob to Alice, well, how does Alice know whether Bob actually sent this or Bob's evil twin Bart? And the way that we do that is that there's a signature from Bob, and here I have fancy fonts that unfortunately don't work, but there's a signature from Bob that says, here, this money is correct. And this signature has the property that if Bart tries to make this kind of fake signature, so it's supposed to be a fake signature, then it's very easy for Alice to tell that a signature is fake. So if I have, more formally, or if I have a so-called public key, I can sign something, some statement, with my secret key, and everybody else can verify that it was truly me, the owner of the public key, or the secret key that corresponds to the public key, that authorized this thing, that gave this signature, and no one else is able to forge a signature. So this is used every single day when you open your web browser and go to your bank. You get, when you see the green lock, you get kind of a signed statement that you're actually talking to your bank, or that you're talking to Google, right? There's a signature from Google that tells you are actually talking to Google, and they're providing the content that you're looking at and not someone else. So why is digital money then difficult if we have signatures? Well, let's think about possible setup. There's some sort of bank that issues 5 Bitcoin to Alice, and it signs it, it gives a signature, and then Alice forwards that money to Bob, and also gives a signature that those 5 Bitcoin or whatever are now in Alice's possession. However, what if Alice does the same and gives this 5 Bitcoin to Bart? Well, the problem now is that if Bob wants to redeem his money and goes to the bank and says, I would like the 5 Bitcoin that you issued to Alice and she sent me, and here are the signatures that all of this would actually happen. Well, the problem is Bart might do the same, right? And then the bank has no idea who actually owns the money. And this problem is called double spending, right? There's, and this is actually, right, you have this it's like if you were able to spend your dollar twice, then, and there was no dollar is lucky enough, you can't spend it twice because you give it away, but that is what prevents this for physical dollars. But with digital money, you seem to have this problem of double spending. So what is the solution to double spending? Well, a simple solution is a global ledger. So say you have this database in the sky that everybody has access to, okay? And Alice has some money, Bob has some money on it, and Bart does not have some money. And then Alice says, send 2 Bitcoin from Alice to Bart, and signs the statement. And then the ledger, the 2 Bitcoin go from Alice to Bart, and it gets updated. And then, okay, seems to be a copy here. And then if Bob tries to send money from Bob to Bart, and this is again supposed to be a fake signature, then it seems like that, it's easy to tell that the signature is fake, and this won't go through. So, and now if Alice tries to send more money than she has, so 4 Bitcoin, then even if she provides a valid signature, then clearly we can see on the global ledger that she does not have enough money to send this. So this transaction is rejected. The interesting thing is, though, that she had enough money in the beginning. She used to have 5 Bitcoin. So what this tells us is that the order of transaction really matters, right? This transaction might be valid, right? She could have sent 4 Bitcoin if this transaction happened first, but because she sent some more money away, this doesn't happen. So the order of transaction is really the key thing that we need to agree on, and it's the same thing in the double spending case, right? Who did Alice send the money first to, Bob or Bart? And we really need to have some sort of record of the order of transactions. So that is the thing that we need to agree on. So how can we make this ledger happen? I said it's some sort of ledger in the sky. Well, we can have a so-called centralized ledger, and basically, nowadays people are calling this a private blockchain, but basically it's a database, right? And there could be a sort of key manager there that has control over the database. And then there are 2 transactions, and the person that manages the database decides which transactions are valid and what the order of the transaction is. So the problem is, of course, that the manager now has a lot of power, right? The manager can censor people. He can say, like, okay, this transaction goes in, this transaction doesn't go in. He also, it's a single point of failure. So if that manager somehow is not available, he goes to sleep or something, then you cannot transact on the blockchain. And so this is rather difficult. But, like potentially a central bank or something could implement something like this. And I would not be surprised if we see that happen at some point. If there's some sort of, centrally controlled blockchain or database by a central bank. But it would place a lot of responsibility and a lot of wait on that one single party. And if it goes down, if they somehow lose their key or whatever, then everything breaks down. So what we would really like is a decentralized ledger. And the first thing that we're going to do is I'm going to give you a potential implementation of what such a ledger looks like, and I'll tell you why this is useful. So this is a blockchain, and why is it a blockchain? Well, basically every transfer, so this could also be a couple transfers, but let's just think of it as every transfer is in a separate block, okay? And every block refers to the previous block using something called a hash function. So this hash function is a cryptographic function that takes a large input and outputs a 32-byte string. Okay, so that's a short string. And the interesting thing is that it's difficult, or it's impossible to find kind of two inputs that hash to the same output. That's a cryptographically secure hash function. So every block contains this 32-byte hash of the previous block, which kind of immutably references the previous block. And so you have this list where every block references this previous block, so you can be certain that, even if you have the final block, then you're kind of back-referencing, or it references back to all the things that happened previously. And in every block, there's some sort of transfers that happen. So, and then finally, you can have, your final hash. And the nice thing now is, so why do we do this, all this complicated thing? Well, the final hash of the final block is 32 bytes. The problem with a decentralized system, right? The problem with the decentralized ledger is that we need to agree on everything. We need to agree on all the, on all the things that happen in it. And it turns out that agreeing on many things is extremely difficult. And especially like in computer science, like agreeing on a large amount of data is also very difficult. However, we can kind of compress the state of the blockchain to this final hash. And this final hash is 32 bytes. So as long as we agree on this final hash, that means that we agree on everything that has happened before, right? So we only need to, this is like, I downloaded, this is when I made those slides. This was kind of a state. If we agree on this hash, then we agree on the state of the whole blockchain, on all the transactions that ever happened. So this really simplifies the problem of agreeing on a global ledger and everybody being in sync of what the global ledger is. And by extension, being in sync on what's the, how much money everybody has and what the order of transactions are. So that is the blockchain design, but that does not tell you yet how do we agree on these 32 bytes, how do we agree on the state of the blockchain. It just makes the problem simpler. So, so basically so there are two questions that are kind of, still open, and one of the questions is like, who adds the blocks, right? Who adds new information to the blockchain? And the other question is, who issues new money, And these questions were kind of thought of as orthogonal questions previously, but then Satoshi Nakamoto in 2008 came along and said that actually we can solve both of these problems by combining them, and by having everybody compete for adding blocks, and as a reward getting new money. So I'll go into a little bit more detail of how this works, but this was the kind of the genius insight that Satoshi Nakamoto, who published the Bitcoin paper, is a pseudonym, we don't really know who this person is, but this person who published the paper, he or she had this insight that we can combine these problems and have people compete for adding blocks, and by that, and get incentivized, and by that make the system work. So, what happens? So, to add a block, a miner has to solve a so-called puzzle. So this is a computational puzzle, and it's described here on the left with a hash function, but basically the best way to solve the puzzle is by randomly guessing, solutions and checking them. And the more often you can guess, the more likely you are to find a solution. But it's a problem that is hard to solve and easy to check. So in some ways, like a Sudoku, right? A Sudoku is easy to hard to solve, but once you have a solution, it's very easy to check that the solution is correct. But it's kind of a solution where the best way to solve it is just guessing solutions. And the puzzle is configured such that on average, one person in the whole Bitcoin network will find a solution every 10 minutes. And of course, this is not real people doing this. This is a computational puzzle, so it's computers just throwing like computation at it. But the more computing power they have, the more puzzles you can try, the higher your probability of solving it first is, and actually it's proportional. If I have 30% of the computation power in the network, then I'll have a 30% chance of solving it first. And this really functions like a lottery, right? And the more computation power I invest, the more stakes I have in the lottery. And the puzzle changes every single block. So there's no, like, if I solve one of the old puzzles, it doesn't help me anymore. I really need to work on the current puzzle to get a current solution and to do something interested with it. And this process is called mining. So why would anybody, try to solve this puzzle? Well, solving a puzzle and publishing a block, and in this block you verify a new transaction, gives the miner a reward. And this reward is newly printed Bitcoin, and also there's some transaction fees. So currently this is, I think, 12.5 Bitcoin, which is $100,000, or was $100,000 when I made this slide. It might be like 3 times as much, or a third of it, I don't know. But the difficulty has, or the amount of money that gets issued, in Bitcoin in particular, other cryptocurrencies are different, it has every 4 years, and what this means is that there's a maximum number of Bitcoin. But this monetary policy is really like specific to Bitcoin and is not an inherent property of blockchains. So why would we do that? Well, so the reason why we do that is because it prevents something called forking. And what we have is the so-called longest chain rule. So if there are two, say there's two, there's Alice the miner and Bob the miner, and they both find a block, okay? So they both, at this roughly the same time, they find a solution to the puzzle and publish, a new transaction. And now there's confusion in the network. Like now, what is the state of the blockchain, right? Everybody agreed up to this point, but then on the next point, people don't agree anymore. So what happens is that, everybody mines on the block that they first saw. So there's a miner that mines here, and then, there's a couple other miners that mine on Bob's block. But in this scenario, Alice happened to get lucky. So her miner, or she, found the next block. And what this means is that everybody is using the longest chain rule. So the miners that previously were mining on Bob's block will now consider the chain that has the most blocks in it. So this is currently Alice's chain, right? It's 1 block longer than Bob's chain. So they will consider this the correct chain and continue adding on that chain. So basically, there was a short time of disagreement, but then the next block kind of resolves that disagreement, and then consensus is reached. And consensus is reached through this longest chain rule. So Bob is sad, and Alice is happy because she gets a reward, but Bob does not get a reward. There was some reward in this block, some newly printed money, but you only get that reward if your block is in the longest chain. Otherwise, your money is lost. You don't get these newly printed Bitcoin, so these $100,000. So even though Bob solved the puzzle, he does not get the $100,000. Only Alice gets the $100,000. So why is this important, right? Why could we not, be fair, split the money, or something along those lines? Well, it turns out that this longest chain rule prevents something called double spending. So say Alice wants to is selling a car to Bart for 100 Bitcoin. And Bart is happy and says the deal. And then Bart includes this transaction for 100 Bitcoin for this Lamborghini or whatever in the blockchain. And Alice receives that money, but she's smart, she knows there could be a disagreement here, so she waits, a little bit just to be sure. And then she hands over the keys to the car. Well, now Bart is malicious, right? And he wants to get his money back. So what he's going to do is he's going to try to produce a different blockchain where his transaction for the Lamborghini is not included and he still owns the money. So he's trying to rewrite history in some way. So, he creates a new block and works for it, and it has no Lambo transaction, and then, he finds another block. But the thing is that the miners, or the rest of the network, follows the honest chain rule. So they still think that this red chain here is the valid chain. So what they're going to do is they're going to extend that chain, and because they have more computation power than Bart, so because there's the majority of the network is honest, in all likelihood they will be the one that exceed or that win in extending the chain. And Bart can try to produce a longer chain, but at the end he's just wasting money and he's just wasting computation power, right? He's working really hard to extend this chain, but no one else considers this chain to be valid. So he's just working really, really hard and wasting money, and eventually, if he's rational and doesn't want to just burn energy, and burning energy means burning money, right? There's a real world cost to solving the puzzle. It's you need to keep your computers running. So if he's rational, then he will just give up and accept his fate. So this longest chain rule is really designed to prevent this thing. So this is, these two transactions are what we call a double spend. So this longest chain rule will prevent it, and Alice is happy because her Lambo money is safe. And so this leads to what I call the Satoshi conjecture. So in the paper, or Satoshi kind of says that as long as 51% of the computation power in the network is rational, and what I mean by rational is that they're self-interested, that they want to maximize the money that they can make, and they maximize the money that they can make by, working, following the rules of the network, and by extending the longest chain. And then basically, he says the network will follow whatever rules we set up. This is not a theorem because it's actually quite difficult to prove and probably not 100% correct. Probably even when you have just 30% of the mining power, you can do some things that are harmful. This gets into a lot of technical details. But still, it holds up in practice, right? We have not seen any sort of deep forks in Bitcoin and people being able to successfully double spend. So this is my introduction to Bitcoin. I want to talk about something that we've worked on here at Stanford and I've personally worked on. So in Bitcoin, all the transaction amounts are public. So you can see how much money is being sent and who's paying whom as well, but especially you can see how much money goes from A to B. The problem is if you're a business, or say you're an employee of a company, and you get your salary in Bitcoin, then everybody can see how much you're making, and that's clearly something that people don't want. And, say in the public supply chain, which is what, people propose Bitcoin to be used for that, this means that, Ford is buying tires from Michelin or someone for Goodyear through a blockchain. Everybody can see how much they're paying per tire, and these are important business secrets. And they don't want to reveal it, and so this having these amounts public really makes Bitcoin and less usable for businesses and private people as well. So what we did is kind of there's this concept of confidential transaction, and this up here is a picture of Venmo. Which is, so the idea of confidential transactions is instead of having the amounts in the clear, we kind of encrypt them. We use a so-called cryptographic commitment to hide the amounts. So the amounts are not publicly visible anymore. They're kind of hidden inside this commitment. And this is kind of what, public or popular things like Venmo, there you can also see who's paying whom, but you cannot see publicly how much is being paid. So I can see, that one friend is paying my other friend for rent, but I don't know how much their rent is. So it seems like something that people want even outside of blockchain. So these confidential transactions achieve this. The problem is, how do we check that a transaction is valid? How do we check that a person who's sending money actually has enough to do this transfer? Well, it turns out that there's a cryptographic tool called a zero-knowledge proof of knowledge, and this is really an amazing thing, that has been around for some time. But it allows you to prove. I can prove you that I know the solution to an equation without giving you any information about what the solution is. So, for example, I can prove to you that I know the solution to a Sudoku without giving you any sort of information what the solution to the Sudoku is. And after the fact, you will be convinced that I know the solution to the Sudoku, and that the Sudoku has a solution, but you have no idea what the solution is. And we can apply the same thing for Bitcoin transactions. So I can convince you that I've had enough money to issue this transaction, and there's no inflation that is happening. I can convince you that the transaction is valid, but you will have no idea why the transaction is valid. So we developed a new sort of zero-knowledge proof system that are extremely small, and they're a lot smaller than the proof system that was previously used, over 10 times smaller, or asymptotically it's logarithmic versus linear, so it scales a lot better. And the nice thing is that this kind of makes these confidential transactions feasible, because it reduces the size of a confidential transaction from, say, 8 kilobytes to something that is around 700 bytes, which is a lot more feasible. And the transaction size really, really matters, because, again, the more complex things we try to get agreement on, the more difficult it gets. So there's really, there's some sort of scalability debate in Bitcoin, or scalability is a huge issue of Bitcoin, because it turns out having to tell everyone in the world about every transaction is actually kind of difficult. So making these transactions small is one of the things that we're working on, and Bulletproofs achieves that while making them also confidential. So this will actually get implemented by Monero, which is the 10th largest cryptocurrency. So I think the goal is within this year that they will actually have, they are planning to implement this, which is really cool, because I personally find it cool, but will reduce their transaction sizes, and it's also kind of really amazing how fast research gets implemented into practice here, right? Like, this is something that was published this year, and within a year will already be deployed in practice and securing multiple $billion, which is currently the value of Monero. So I want to point you, if you want to know more about the research that we're doing at Stanford, I want to point you to the site, which is crypto.stanford.edu/C2RG. That's the cryptocurrency research group, which is a part of the group that I am, or there's also my private website. So yeah, thank you very much. Are there any questions? Okay.
Is there a way to not only hide the Vietnamese cent, also the public contract of the sender and the receiver?
Yeah, so that's a very good question. So the question was, I'll repeat it for the video, whether you can also hide the sender and receiver. So confidential transactions do not do this. There is a cryptocurrency called, there's basically, Monero does this in some sort of other ways. In some ways it's an orthogonal problem, and Zcash is another cryptocurrency that does this. It turns out that doing this is a lot more difficult in some ways. So you have to use heavier cryptography with worse assumptions, kind of, or there's, yeah, I could get into more details in that offline, but there is ideas of how to do this. Okay, just maybe one more question. Yeah.
So there's a recent paper by, I think it's from Yale, talking about normalizing the linkability of the Monero. So I think they get recover like 60% or whatever the transactions. What's your take on that?
Yeah, so I think this is, there's multiple people working on this. The question is, there's a paper on de-anonymizing Monero, and yeah, I think it's a very interesting and good paper, and the problem is kind of in Monero, you say, I'm spending one of these K coins, so maybe one of these 5 coins, or one of these 10 coins, and the problem is that the values, if they're too small, then through kind of very smart interception attacks and intersection analysis, it turns out you can actually often check who is paying whom. And for example, in Zcash, you get the better kind of privacy, which is this is like one of all of the coins that have ever existed is the coin that I'm spending. So you really don't reveal anything about the coin that you're spending. The problem is, again, this comes at a higher kind of cost in terms of the cryptography that has to be used and the assumptions that we have to use. There's the so-called trusted setup. But yeah, so it's a very interesting paper, and I think it's definitely a concern. So, yeah, thank you.
I'm sure you have a lot of more questions about blockchain and you wanted to ask Benedikt. And we do have time after the event to have private talks and meetings.